little bit of background, and I will not spend a lot of time on the issue at hand, just provide some context, but there is a big issue when it comes to, so in the field of civil engineering, which is associated with the damage of marine structure, such as bridges and any other structure that actually has its foundation in the seawater or near the seawater. In the marine environment, due to the diffusion of chloride in reinforced concrete, there is a corrosion taking place in the rebar, which causes damage in the structures. And the effect is that you can see to the right, a bridge with the foundation of the bridge right here, and it's literally outside of my building. This is over in Port Everglades in South Florida, and you can see the intracoastal waterway. This is some brackish water over here, and you can actually see in this picture and on the next one as well, but the concrete is undergoing damage. What happens is that the rebar expands due to corrosion, cracks the concrete, and if this is not undergoing on regular maintenance, repairs are necessary and the cost becomes significant. So now, let me just, I get a few messages once in a while of people wishing to participate, so I will let you join in as it comes. Second, here we go. Now, in terms of what is physically happening, Florida bridges are actually prone to chloride-induced corrosion once chloride threshold is reached. And in a partially immersed situation, such as the piling of bridges in the marine environment, the chloride ions are going to penetrate from the exposed surface into the rebar. Now, the rebar underneath is going to actually start to corrode once a critical level of concentration is reached in and around the rebar. Now, for the detail on this, I would send you to the presentation by my colleague, Dr. Preswell, who presented a couple of months ago, and his presentation should be, I guess, on the WSU website. I am personally an acoustician, not a chemist, and as a result, I do not go into a whole lot of detail on this process. Now, what is important, however, is that the initial corrosion sites can be as small as a pit, and interactions of corroding site with surrounding steel is going to affect how the corrosion propagates. Now, the result, again, if not handled, can actually be significant damage in the reinforced concrete, with literally pieces of reinforced concrete falling off in the water. Now, there are techniques to actually mitigate this using blast furnace slag, fly ash, and silica fume, which are three of the admixtures commonly used to reduce concrete chloride diffusivity. Now, by admixtures, we mean that when the concrete is actually mixed, these materials like blast furnace slag is added to the mix. But here, really what we intend on doing is not mitigate this corrosion effect, but detect and identify it early. And there comes my field of specialty, which is underwater and high frequency acoustics. So the idea is this: the detection and measurement of rebar corrosion in reinforced concrete using ultrasonics non-destructive testing, which is labeled usually as NDT, has been of great interest for several decades. The benefit is obvious. Using ultrasonic NDT, the operator can monitor corrosion in reinforced concrete and ideally detect early signs of corrosion without any need to drill through or cut the concrete, which is a costly process and quite often highly impractical. The limitation of this approach resides in the ability to successfully detect early forms of corrosion before cracks reach the surface of the reinforced concrete. Now, before I continue, just a little highlight. High frequency acoustic cannot produce images or data of quality comparable to that of photographic imagery. So the data need a lot of processing, a lot of analysis to actually be really fully understood. Now, in order to understand what these ultrasonic data give us, there's been a lot of work done. So recent publications, and I provided a sample of this over here, indicate that the scientific community is testing a variety of signal processing approach to accurately estimate the propagation of cracks and changes in the rebar diameter, which is associated usually with corrosion, typically using narrow beam broadband acoustic transducer, such as transducers operated at hundreds of kilohertz with millimeter scale resolution. Now, the approaches that are used include usually higher order statistic, short time Fourier transform analysis, artificial neural network, convolutional neural network, wavelet decomposition, empirical mode decomposition, and Laplace transform. In particular, these days, one of the big efforts is in CNN and anything associated with deep learning algorithm, and which are actually showing promising results. Such state-of-the-art techniques have great merits, but they are limited in three specific ways. The first limitation is this: early crack detection capability depends on spatial resolution. And early crack capability is important because we want to be able to figure whether there is corrosion taking place at a very early stage so that we can very quickly take measures to prevent further damage. The techniques presented in the previous slide mentioned in the previous slides and in this type of references over here, rely one way or another on distance measurement obtained from the time of travel of sound and an estimate of the sound speed in the concrete and rebar. Now, propagation of ultrasounds through concrete is subject to great attenuation, mostly due to friction and signal scattering. And such attenuation increases significantly with frequency, while spatial resolution improves as frequency of operation increases, thus increasing the effective bandwidth of the transducer. So there is an issue here. If you want to actually get a better spatial resolution, the sound cannot actually get in as far in the concrete. The result, ultrasonic transducers used to monitor reinforced concrete are often operated around 500 kilohertz, which is going to be the sweet spot in frequency where you get the best compromise between pretty much the range of operation, how deep the sound can go in the concrete, and how good a frequency and spatial resolution we can get. So that the sound can travel, for example, at 500 kilohertz through several centimeters of concrete, reach the rebar, and produce a sufficiently strong echo. All of this with a resolution of the order of 5 to 15 millimeters, depending on the transducer frequency bandwidth and the actual speed of sound in the concrete. Now, note one thing, many of these techniques exist. Okay, many techniques exist. I mean, like shear probe, contact transducer, focused and unfocused immersion transducer. Okay, and the angle of observation can be adjusted. So that actually helps getting the best out of the transducer. But the fact is, it remains that the resolution is not sufficient to observe cracks a few millimeters long or less. That is, if we have a crack which is like a quarter of a millimeter long, these transducers will not be able to create an image of sufficient resolution to depict it. So that in turn, it limits the ability for an early detection. So early detection is actually limited by the physics of acoustics and the physics of transducer operation. Now, the second limitation is going to be that early crack detection capability depends on the meaningful training of the crack detection algorithm. And I'm bundling it with the third limitation, which is that early crack detection capability depends on the complexity of the sound propagation model we refer to. Now, these techniques that I mentioned a couple of slides ago require either algorithm training, for example, in the case of ANN and CNN, through observation of damaged samples, or an acoustic propagation model. Now, please bear with me just 1 second over here. Here we go. In the second case, the case of the second limitation mentioned over here, the performance of the approach depends heavily on the number of training samples available and is limited to the statistical representativity of such samples. Considering the millimeter scale resolution of the transducer, the highly anisotropic nature of concrete, and the strong variation in shape and composition of the corroded areas, such statistical representativity can be only achieved through very large number of concrete samples. That makes it impractical because when we work, for example, on a bridge, we may only have a handful of samples we can use. Now, in the third limitation, which is listed over here, the published approaches rely on simple acoustic models to translate the acoustic signal into actual estimates of the actual damage occurring in the rebar and in the concrete. Now, there are techniques or modeling techniques such as elastodynamic finite integration technique, or FIT, volume scattering models, and finite element analysis tools such as COMSOL and analysis, which are commonly and extensively used. Now, while such techniques have great merits and are very well established, they produce results of great quality, but they rely on the purely elastic model, which has limitation, especially when it comes to the dispersion of the response of the system. In plain word, the system, the sound propagation through the concrete and over the rebar is frequency dependent. As frequency changes, so does the response of the system. And most of these models have a very limited way of modeling this frequency dependence of the response of the environment. Now we move to the next slide. Now, some observations clearly indicate that in the vicinity of the corrosion and crack, there is a complex structure combining fluid cavities and loose concrete material surrounding the corroded rebar. This means that a more appropriate acoustic propagation model could be a poro-elastic model, such as the well-established BO and BO-stall models developed for the propagation of sound in the seafloor originally. But at very early stage, BO also did some work in reinforced concrete and concrete structures as well. So the model is relevant. In both cases of the BO and BO-stall model, fluid-filled cavities and the skeletal frame produce coupled vibrations induced by the incoming sound, resulting in a dispersive medium where two types of compressional wave, the fast and slow wave, in addition, shear waves, propagate. So that actually is a more complex and more complete model showing how sound moves and travels through concrete and reinforced concrete in general. Now, the frequency response of a poro-elastic medium is going to be different from that of a traditional elastic or viscoelastic medium, which is usually what is modeled using techniques like FIT, COMSOL, ANSYS, and so on. Now, to conclude with the problem statement, the BO-stall model, which is actually at the root of what I am presenting here, although complex, has a great benefit of tying the physical property of the porous medium, such as porosity, mean grain diameter, mass density, bulk and shear moduli, and so on, to the sound propagation through the porous medium. As such, it is possible to fit a set of physical characteristics of the medium to a specific acoustic signature measured of the transducer. While the BO-stall model has been extensively used for foundation engineering and naval purposes over the past 50 years, it has not been applied to this problem studied here. There has been some attempts to do it, but not in the context of early detection of cracks in reinforced concrete structure due to chloride-induced corrosion. So in addition, the author has studied and published a specific technique, that would be me, derived from the initial work by Stern to handle gradual changes of the physical characteristics of the medium and produce a synthetic response of such porous medium to a broadband acoustic impulse. Now, such a model can handle the propagation of sound through a pure fluid a solid, and a corroding porous medium. And I will show I will show a diagram that explains how things are actually layered. Now, this technique is very relevant at the acoustic frequencies used, that is around 500 kilohertz, and in material observed around the corroding rebar. Now we have stated the problem, and that was quite extensive. Here is the project goals and objective. The goal of this project is to demonstrate the ability to detect early appearances of cracks in reinforced concrete due to rebar corrosion using ultrasonic non-destructive acoustic testing with no direct contact between the sensor and the concrete block, in conjunction with a Poro-Elastic ultrasound propagation model originally developed by the author for sediment application and adapted for corrosion and fracture in reinforced concrete. The objectives are threefold. Number one, to identify the proper measurement configuration and predict the performance using the modeling of ultrasound propagation in the reinforced concrete. Two, to perform a series of targeted measurements using the proper ultrasonic transducers on a set of existing reinforced concrete samples placed in partial or complete immersion. And three, to evaluate the degree of corrosion within the reinforced concrete with confidence level according to the Poro-Elastic model, and correlate this result with those obtained with traditional non-invasive technique, such as corrosion current and corrosion potential measurements. Now, I would like to mention right away that today in this talk, we are going to focus on objectives 1 and 2. We are working on objective 3, which is providing a degree of corrosion and statistical information, but that actually involves ongoing measurements, which are pretty much taking place right now. So I'm going to focus on the presentation of the model and some of the measurement and show that model and measurement really match and lead us to a set of physical parameters that is appropriate for the concrete and the reinforced concrete, I should say, concrete and rebar. Now, this research in the long term will be the foundation for a more detailed acoustic analysis of rebar corrosion detection in reinforced concrete pilings and columns out in the field. The methods outlined here could be developed to the degree where early post-cracking corrosion could be detected in the field. And also the detection of pre-cracking corrosion would be likely. Now, we will see soon that post-cracking is actually a simpler problem, clearly. Now, here's the approach. The overall approach is depicted in figures 1 and 2. So here are figures 1, which is the experimental setup, and figure 2, which actually provide the process of the ultrasonic detection of rebar corrosion. So let me go over some text first, and then I'll go over the figures. The approach consists in analyzing a limited series of reinforced concrete samples provided by the corrosion laboratory of Dr. Preswell Moreno at FAU, using a narrow beam high-frequency submerged transducer operated at 500 kilohertz, powered using a transducer, which is an Olympus Panametrics V389, connected to an HP8112A high-frequency impulse generator, and where the data are collected using a digital oscilloscope, Tektronix DPO3014. And the reason for this choice is that all these transducers were readily available in my laboratory and in the electronics laboratory in my department, so there was no cost associated with purchase. Regarding the detection ability in the field, two aspects must be considered: the transducer aspect and the signal processing aspect. It is understood that a submerged transducer is not necessarily the most practical choice in field operation. Now, the reason why we went with a submerged transducer is because number one, it's a good choice. Number two, the transducer was available, but contact transducers are a better solution. So in the longer term, we intend on testing the approach using a contact transducer. It will not modify the proposed approach I show here, which is entirely based on the acoustic signature of the signal as it travels through the concrete and to the rebar. But what the contact transducer will do is provide better quality signals. Now, regarding the signal processing aspect, we must keep in mind that the V389 immersion transducer is operated at 500 kilohertz with a pulse length of 7 microseconds, which actually corresponds to a range resolution of nearly 16 millimeter, using an estimated 4,500 meters per second for the compressional sound speed in concrete, while the acoustic wavelength is 9 millimeter. This is an unfocused transducer, which has a beam width of 14 degrees at -6 dB in the concrete, which corresponds to an across range resolution of 12 millimeter. So what does this mean in plain word? In plain word, it means that if we were to use this transducer solely for the purpose of imagery to find a concrete flaw, this transducer would cover a fairly wide area over the rebar and would not be able to create an image with a resolution of less than approximately 9 to 12 millimeter, which corresponds to a significant crack already. However, the model itself can actually lead to earlier detection of the crack. So is the intent. Now, here's the experimental setup. The tank is over here, and we'll see a picture in a minute. In the tank, we have our concrete block with the carbon steel rebar over here. We see it from the side. The long bar axis is X. The vertical axis pointing downward is Z. So in this side view, we can see the transducer, which is partly submerged in the salt water. The concrete rebar is fully submerged. Now, the cone of acoustic emission is originally starting from a set location along X. It is right over the rebar, as you can see from the front view to the right. The distance between the face of the transducer and the top of the concrete block is D. The depth of the rebar is H. And what happens is that we actually move along the transducer along the X-axis while keeping the position along the Y-axis, which is shown over here, constant. So we pretty much line up the displacement or the position of the transducer with the position of the rebar. Now, in terms of signal generation, the signal generator produces a 7 microsecond pulse at 500 kilohertz, 10 times a second. The signal is transmitted, and then this transducer is a reciprocal transducer. The sound is going to travel through the cone to the concrete. Some of it is going to penetrate in the concrete, reach the rebar. Some of it is going to be reflected off the rebar, travel back through the water, and reach the transducer again. So we're going to have a series of echo, a surface echo from the concrete, an echo from the rebar. And then after that, we will have multiple bounces that are going to add to the signal generation. But the first three signals received, I'm sorry, the first two signals received, I should say, are going to be the echo from the concrete surface and the echo from the rebar over here. Everything else will come afterward. Now, these signals are going to be received and digitized using our oscilloscope. The signal will be very highly oversampled at 1.25 gigahertz and stored so that we can afterwards process them offline using a laptop. And all the processing is done in MATLAB right now. Now, I would like to mention that the model runs very, very fast, very quickly, so that real-time operation is absolutely not a problem. Now, in terms of the operation, I describe in here how things are going. So we have two operations taking place in parallel, the data acquisition and the modeling. So let's start with the data acquisition. We precisely place the transducer over the rebar at fixed value of Y, and we actually move the transducer at various locations along X. And typically, we move the transducer by 5 millimeters at a time. At every location, we acquire, as of now, 10 records and sum them together after careful time alignment to reduce the electric noise, both in band and out of band. At the same time, we establish a set of default physical parameters for the seawater, concrete, and rebar, and we calculate the theoretical noise-free acoustic response using the Poro-Elastic model, assuming either homogeneous layer or gradual changes in the physical properties versus depth. Now, I would like to mention that the assumption that we have a noise-free environment is a reasonable assumption, as the transducer itself is very quiet. The acquisition system itself is very quiet. And we actually work in an environment where there are very, very few vibrations. So the signaling tends to contain relatively little external noise or electrical noise. Now, after that, both in the measurement and the model, we identified the first concrete echo and the first rebar echo using time gating. We actually knowing the position of the surface of the block and the position of the rebar, we can have a fairly good idea of where the echoes should be located by having a notion, at least, so a good approximation of the speed of sound in the water, in the concrete, and in the rebar. Now, the next thing we do, we actually combine model and measurement to verify that the default parameters produce a reasonable match in terms of time alignment, and echo amplitude of the echo at the concrete surface and in the rebar. And we establish a value interval for every adjustable physical parameter. By default, these parameters will be in the concrete, the porosity, mass density, bulk modulus, shear modulus of the poro-elastic material. In the rebar, it would be the mass density, modulus of elasticity, and the distance from the top of the rebar to the bottom of the concrete block. And afterwards, we actually use a nonlinear solver. Right now, we use the truss region reflective algorithm or the Levenberg-Markov algorithm to adjust the physical parameters so that the least square error between the measured and simulated echoes, that is the first concrete echo and the first rebar echo, is minimized. Afterwards, we record and analyze the change in physical properties in both concrete and rebars from one acquisition to the next to identify trends. We compare these trends against the corrosion potential measurement and repeat the process at fixed period. By default, that will be once a month. Now, once we're done with that, we pretty much go back here in the data acquisition and modeling. Where are we here? We have completed the blue and orange section right here, which is modeling and measurement. And we actually perform the time alignment. And right now where we are is we are working on the nonlinear solver. We've implemented the nonlinear solver, we optimized the parameter, and we are currently in the process of acquiring more data with new samples to identify trends. So in many ways, the completed work is in the top half of this diagram, and the ongoing work is the bottom half. Now, regarding this approach, using this transducer, pre-cracking corrosion would translate into two phenomena: a change in the characteristic impedance of the rebar in contact with the concrete, causing predominantly a change in the amplitude of the rebar echo, and a change in the diameter of the rebar, which would produce a change in the time of travel difference between surface echo and rebar echo. Using this transducer, post-cracking corrosion would translate into two phenomena as well: an accentuated change in the characteristic impedance of the rebar in contact with the concrete in comparison with the pre-cracking corrosion case, and which in turn would be causing predominantly an accentuated change in the amplitude of the rebar echo. The second phenomenon would be that we would observe an additional echo due to the presence of forming cracks. Differentiating in time between the cracks echo and rebar echo would be difficult due to their proximity. However, post-cracking corrosion would also result in a very different signature from pre-cracking corrosion, which in turn would generate significantly different matching parameters in the Poro-Elastic model. And for this reason, when it comes to the level of difficulty, post-cracking corrosion is going to be much more likely to be detected and identified than pre-cracking corrosion would. So we are focusing right now in differentiating between what would be a virtually perfect sample with no corrosion and what a sample would produce when early signs of cracking are actually taking place. Now, again, detection and identification of pre-cracking corrosion is expected to be more challenging than that of post-cracking corrosion. Now, here's our progress to date. We have completed the development and testing of the Poro-Elastic model for the reinforced concrete sample. We have actually collected data on the limited number of reinforced concrete samples using the system we described below, before, and this setup is shown in figure 3. So actually, you can see it over here. Here's an example of a sample. This is the face of the transducer. This is the reinforced concrete sample over here. We place the transducer 12 centimeters over the surface of the concrete to ensure that the transducer is operated in the far field so that we do not have near field interference issues. We can see it from the side, and this is the view from the top. As you can see, we align the transducer carefully relative to the rebar and actually move the transducer along this direction over here. A sample of experimental results is shown in figure 4. Now, in that, the transducer was carefully placed on top of the corroded rebar and moved along the axis of the rebar in increment of 5 millimeters. The initial position was 2.5 centimeters off the edge of the concrete block. And I would like to mention that our position along X is measured relative to the center of the transducer. Now, the last position was at 9.5 centimeters of the edge of the concrete block. At every position, 10 acoustic signatures were recorded. Then, in order to reduce electric and thermal noise contained in the high frequency measurement, the acoustic signature was averaged across the 10 measurements. So that's what is shown in figure 4. Now, in figure 4, what happens is that we are showing the impulse response measured with the acoustic transducer as a function of the time delay scaled in microseconds. The impulse response is actually a measurement in volts. It is not scaled in micropascal. It's a volt measurement. And along the second axis of this waterfall over here is the position of the transducer along the x-axis, all the way to 9.5 centimeters, starting at 2.5 centimeters. And these measurements were actually performed on March 5th of 2021 in this example. Now, processing of simulated data sets and comparison between simulated and measured data were also completed. In figure 5 and 6, we show an example of measured versus simulated acoustic signature using the parameters listed in table 1. The table coefficients were obtained from concrete sample information provided by Dr. Preswell and from the literature. And the results really clearly indicate that the model and the measurements match closely. So here we are. Here's the set of parameters. So the parameters we actually use for the saltwater are the mass density, phase speed, and bulk modulus. For the concrete, we assume that we have a 16.6% cementite, 33.4% sand, 43.1% coarse, and 6.8% water mix, under assumption that the sample is saturated with fluid, and we're talking about salt water here. Now, the bulk modulus of the concrete material, the mass density of the dry concrete material, the fluid viscosity, the porosity, the permeability parameters are used to model the concrete. In addition, we also model the pore size parameter, which I explain a little later, the dry concrete shear modulus, the Poisson ratio of the dry concrete, the mean grain diameter, and we also account for 3 other parameters, which are the shear logarithmic decrement, the bulk logarithmic decrement of the wave, and the bioacoustic, the BO added mass coefficient, which is a added mass coefficient which accounts for the mass loading of the skeletal frame by the fluid. In the rebar, we model the mass density of the rebar, the phase speed in the rebar, and the depth below the concrete surface. So all these parameters were in the results I'm showing here. We were actually using a set of pre-selected values, which are reasonably close to reality, but not optimized. And then currently, my student, Matthew, who is co-author on this paper, is actually working on optimizing the value of several of these parameters using a TRR, nonlinear solver. Now, figure 5 shows a sample, an example of the echo measured at the water concrete interface in blue, and lined up on top of this echo, we put the concrete rebar echo measured by the transducer. So that's an overlay plot, okay? And that was for the when the transducer was placed 2.5 centimeters from the edge of the concrete block, and this result was averaged over 10 measurements. Now, just so that I relate this to this measurement over here, this, if I circle over here in this diagram in figure 4, this is the transmitted pulse. This over here, after about 10 microseconds, is going to be the echo from the concrete block. And right here, this faint echo after about 17 microseconds is the reflection of the rebar. So again, transmitted impulse is the first one at 0 microsecond. Surface echo is going to be at 10 microsecond, and rebar echo is going to be at approximately 17 microsecond. And there are other echoes afterwards, multiple bounds and the like, but through time gating, by carefully time selecting the signal, we can focus what would be the portion of the signal that corresponds to the surface of the concrete block echo and the echo over here associated with the rebar echo. So in this last plot in figure 6, what I'm showing is a comparison between measured and simulated results. In blue, it's going to be the concrete and rebar echo obtained using the average across the 10 ultrasonic signatures. And in red, we are going to see the Poro-Elastic model simulation result for the same configuration using the parameter listed in table 1. Now, a few clarification regarding the experimental results to date. To clarify figure 6, the focus is both on the surface concrete echo and on the rebar echo. There is an excellent match in amplitude and time signature at the concrete surface between model and measurement, which indicate that the Poro-Elastic model uses a representative set of physical parameters. In plain words, it means that the Poro-Elastic model I'm using is doing a pretty good job given the set of physical parameters we actually used for the concrete and for the rebar. These parameters being very, very close to what we believe to be the actual values. Now, the model and rebar echo match in time delay and amplitude. As we can see over here, there is a good match between the red and the blue in both cases, but there could be a better match for the duration of the rebar echo, which is over here. We notice that the BO simulation indicates that the rebar echo should last a little longer and should be just a tad stronger. Such a match in time delay and amplitude is an important indication that the physical characteristics of both rebar and concrete are representative of the actual samples. The second half of the rebar echo is much more pronounced in the model than in the measurement. And there is a reasonable explanation for that. That reasonable explanation is that for this observation, there is interference from a secondary echo produced by the rebar itself. So let me just go back on the slide and explain what I mean by this. What happens is that as the sound travels in the concrete and hits the rebar, sound is actually going to travel through the rebar and create a secondary echo at the bottom of the carbon steel rebar. The model we're using is focusing solely on what is happening in the concrete above the rebar and through the first and with the first echo of the carbon steel rebar. But the carbon steel rebar is relatively thin, and as a result, there could be an interference from the secondary echo coming from the bottom of the rebar, which currently we do not model. So what we're going to do, let me just go back to my comments over here. In the model used here, only one echo is produced at the interface between concrete and rebar, when in reality, the elastic rebar produces multiple echoes, as I just explained, as sound travels across both the diameter and circumference of the rebar. Since the rebar has a diameter of 16 millimeter, the next and most significant secondary echo is delayed by nearly 5.8 microseconds. Now, at present, in addition to the work we are currently doing, we plan on accounting for the total thickness of the rebar in the Poro-Elastic model in order to produce a better match in the acoustic signature of the rebar. But still, as is, the match between the measurement and the model is of sufficient quality that we should be able to identify early cracks as they form. Now, let me ask very quickly, Cheryl, how much more time do I have?
Ten more minutes, I guess, for
10 more minutes.
Yes. Sorry,
okay.
I was muted. 10 more minutes.
10 more minutes. Okay, very good. So what I'm going to do is I'm also going, there is an entire part of this presentation associated with the model itself, and it will be available. People who are working in the field of acoustics can certainly read it. I provide a whole lot of equations, but I will actually focus more on the result and some of the conclusion, given the fact we have only 10 minutes left. So about the experimental results to date, I mentioned that we are currently in the process of running measurement on additional concrete samples. So figure 7 shows a new set of reinforced concrete samples showing various levels of cracking due to corrosion. And you note that in this new concrete sample, we have 2 rebars which are actually detached, one at the top and one at the bottom. And from the left to the right, we have different levels of cracking taking place. So here's the thing, this new set of concrete samples showing various degrees of cracking have been identified and are currently used, and a series of rebar potential measurements have been performed to verify that corrosion is indeed taking place. Now the concrete samples are numbered from left to right as rebar 1, 2, and 3. I'm sorry, as sample 1, 2, and 3. And in each sample, so sample 1, sample 2, sample 3, and in each sample, the top rebar is rebar 1, and the bottom rebar is rebar number 2. Now, the cracks in sample 2 and 3, and center and right, and to the right, are the result of the corrosion of the rebar beams embedded in each of the samples. Note that the rebar extends approximately 25.4 centimeters inside the reservoir, and each rebar has a diameter of 1.6 centimeters, yielding a surface area of approximately 128 centimeters square, including the area at the end of the rebar that is available to corrode. Now, the samples are actually stored outside in the marine atmosphere and literally next to salt water, and brought indoors to gather the parameter E, R sub S, and I core, which are measured in the corrosion lab. Now, before rebar potential measurements were taken, the samples were damped using a sponge and allowed to sit for some time, and a galvanostatic pulse, GP, approach is used to obtain the parameters R sub S and I core 1 week after the samples are placed indoor. So here are the values that are actually found as a function of the sample number and the rebar. So these are the coefficient E core in millivolt, RS in kiloohm, I core in microamps, and the last term, which is lower I core in microamp per centimeter square. Now, I do not have time to provide the detail of what these coefficients mean, but they are quite common in the field of potential measurement. And what I want to focus on very quickly in this measurement is this plot right here, which actually shows the rebar potential, which is called BSC, as a function of the distance along the rebar, which in this diagram is shown in inches, for the different samples, sample 1, 2, and 3, and for the different rebars. Now you remember sample 1 shows very little corrosion, sample 2 is actually subject to some cracking, and sample 3 is really badly cracked. So you actually can see in black and red that really a lot of corrosion is actually taking place in both samples. So I can read what is actually provided over here. Preliminary rebar potential measurements on new concrete sample using saturated calomel electrodes are leading us to the following conclusion. Based on ASTM standard values, rebar potential less than minus 0.28 BSCE indicate high probability of corrosion taking place. And that is pretty much what is happening in rebar number 2 for sample 2 and sample 3, more or less. In particular, this one right here, the red circle, which would be rebar 2 sample 2. And corrosion is likely to be highly localized, which would account for the variation of the rebar potential values along the length of the rebar over here. So you notice that the potential value changes as we actually change the length or the distance along the rebar, I should say, which actually is due to the fact that we have highly localized corrosion. Now, I would mention for these 2 slides, this is predominantly the work performed with the help of Dr. Preswell, and this is his field of specialty. What I want to get out of this is that those 3 samples, according to the potential measurements, clearly indicate that we have gradual increase in the corrosion in the rebar, which would indicate that these 3 samples would be good candidates to actually look at the difference in signature when it comes to corroded rebar versus non-corroded rebar using ultrasonic testing. Now, given the time that is given to me, again, as I mentioned a minute ago, there is an entire section labeled methodology where I actually explain what the poro-elastic parameters are. But I just want to just take a minute to use this little diagram here to show the model we actually use for acoustic modeling. So we assume that we have a water volume made of salt water with 10% of salt by unit of mass. And we actually model the reinforced concrete as the concrete, which is going to be a combination of aggregate and cement, where there are areas where seepage can actually take place. This is where the fluid can actually seep. And below that is the rebar. And as pretty much chloride reaches the rebar, corrosion starts taking place. This is the model we use. Now, again, we use 14 physical parameters in the Biostall model, or the Poro-Elastic model we use. And we match all these parameters to using a comparison between the model and the measurement we make. We pretty much match the modeled acoustic signature and the measured acoustic signature to identify the value of these parameters. And these parameters, the value of several of these parameters will change as crack is taking place. Now, in the methodology, I provide all the equations, the fundamental equations associated with the model itself. So again, if you are very interested in the physics associated with this model and the mathematic foundation of this model, everything is provided over here, but I unfortunately do not have time to cover it today. It is a fairly involved model, much more complicated than a traditional viscoelastic model. But at the end of the day, what we obtain is the response using this model, which is actually shown in figure 6 of slide 19. Now, let's jump to the conclusion, given the little time we have left. In terms of conclusion and ongoing work, I mentioned first that there is some improvement needed in terms of matching what the model produces and what we measure, in particular when it comes to the secondary echo coming from the rebar. Now, I would like to mention, and that is going to be at the bottom of my conclusion right here, that's really important one, is that as we speak, we are actually testing the nonlinear solver based on the trace region reflecting algorithm to refine the physical parameter of the acoustic model in order to improve the match between the model data and the measured data. And in addition to that, we are performing ongoing acoustic measurement with the new 3 samples that I showed in the previous pictures. A sample with very little corrosion sign, a sample with some amount of corrosion in the rebar, and a sample with severe corrosion. And these samples are undergoing acoustic measurement, and we are in the process of matching the measurements we made with what the Poro-Elastic acoustic model would predict. So this is the stage we're in. And with that, I will conclude with some questions. I believe there are probably some questions coming from the chat. And I would like to acknowledge before I end the fact that the National Center for Transportation, Infrastructure, Durability, and Life Extension has been sponsoring this project. So thank you very much to Tri-Durally for their kind support. And also Washington State University, WSU, for allowing us to actually do this work. I would like to also acknowledge my colleagues and the support of the Department of Ocean and Mechanical Engineering at Florida Atlantic University. And I would like to mention that while we're indebted to both institutions for their financial support, we also appreciate the assistance with the laboratory work by several graduate and undergraduate students who helped us put together the samples. The opinions, keep in mind that the opinions expressed in this paper and in the reports are those of the author and not necessarily of Tri-Durally. So we have come up with some of our own conclusion based on our measurements. And with that, that concludes my talk, and I will open the floor for questions.
If anyone has questions, go ahead and speak up or type them in the chat room.
Thank you. Yeah, very interesting presentation. I have one question. Maybe I didn't quite get it. In the introduction, you mentioned there's a lack of spatial resolution for some of the existing approaches.
Yes.
So how is the spatial resolution of this one you're proposing?
Well, I'm going to answer another way. Spatial resolution is less relevant in the method I am using. The spatial resolution of the transducer I use is of the order of 9 millimeters, which is not very good. The best transducer you can use for the work at higher frequency and maybe give you a spatial resolution of the order of maybe 4 or 5 millimeters. But the model I use is detecting the crack based on a match in really the frequency domain of the response of the signal. So let me just go back a little bit on slide 19 very quickly. What happens is that you see there is the blue signature measured and the red signature, which is modeled. To actually get a match of these combined echoes, you need to actually perform a match one frequency after the next of the response of the medium to the acoustic signal we transmit. So it is not about a spatial resolution as it is a change in the spectrum of the echo, which back in time is translated into a sequence of a surface echo and a rebar echo separated by not only a very specific time, but the shape and amplitude. So to answer your question, we do not actually look at the very specific time alignment of echoes to create an image of what's happening in the concrete as it is traditionally done. This requires sub-millimeter resolution. We actually use the frequency response of the medium to a broadband signal and see how this frequency response really changes. And I did not have time to show how the spectrum changed over the course of time, but this is actually information I have. I can certainly provide offline if you want to.
Thank you for the clarification. I do have a follow-up question.
Yes.
Which is, with this approach, would you be able to detect early age cracking, which may be only like 200 microns and propagating, in the early stage?
we should be able to, and for the following reason, is that the cracking itself is actually producing a change in the acoustic and mechanical impedance of the medium at the interface between the concrete and the rebar. And that actually causes a fairly significant change in the signature of the response. So that should produce, and our current operation, our current measurements and simulation indicate this is the case. This should occur, we should produce a noticeable change in the physical characteristic of the medium so that we can actually match what we measure with what we model. So the answer is most likely, but we're working on it.
All right, thanks. Would we be able to differentiate the cracking, say if it's macro cracking in the concrete matrix versus cracking closer to the rebar, like a debonding?
That is, I'm not sure I can really answer this question yet. We would actually have to place ourselves in the two different scenarios and see if the acoustic response and the model can actually produce different characteristics of the physical parameters of the concrete block and rebar. So the answer is it's likely, but I do not have any material to actually support this at this point. It's too early in the project to do that, to say that.
Thank you. Yeah, go ahead, Dr.
Question. Pierre Philippe, thank you very much for this interesting presentation. I wonder if you have tried to correlate the method you're using with Faraday's law to measure the percent mass loss. I'm sorry, I missed the early part of your lecture. I was in the class.
The percent mass law is actually very interesting because my colleague, Dr. Preswell, has been doing some work with one of his students in that field. And the answer is we're very interested in this for the following reason, is that it actually would provide us with a better idea of what the porosity would be in the medium. And the porosity in the concrete medium is actually a very significant parameter. It actually drives a lot of the other physical parameters. So the answer is we've been actually looking at other physical, other technique of measurements of the concrete characteristics within the concrete to try to find a better initial set of physical parameters, in particular the porosity in the case you're talking about. And also a valid range of fluctuation of these parameters. So this is how I will answer it. It is a correlation in the sense that we try to better tune our model parameters this way.
Thank you.
Any other question?
I don't see any other questions for you, Dr. Beaujean.
Well, thank you very much. And Cheryl, I guess this presentation will be available somewhere on the website for people who want to look at the model itself.
Yes, absolutely. This recording will be put on our Tri-Delay website, and it takes a few days to edit it and get it online. So you should be looking next week for that online. And thank you so much for your presentation. And we really appreciate everyone who's joined us today.
Cheryl, the project report is also already online, right, on the Tri-Delay website?
That is correct, yes. If you look under the research tab on the left in the navigation, you'll be able to read the final report of this project.
Well, thank you for your time, and thank you for listening to this talk today, and I wish you all a good day.
Yes, thank you, everyone. Have a good day.
Bye-bye.
Bye now.
Bye.
Bye-bye.